Hello, everyone. It's already 9:30, so it's time to start our webinar. Thank you for joining us today in this Wednesday morning. First of all, let me introduce myself. My name is Aleksandra Radwańska. I'm the International Business Development Manager in the team of VPP Business Solutions and Services at Next Kraftwerke. I'll also shortly introduce Next Kraftwerke to you before we start the content part of our webinar. So probably some of you already know and you're familiar with our company. Probably Next Kraftwerke to some part of you is new. So first of all, Next Kraftwerke operates the second biggest VPP, so virtual power plant in the world. And at this moment, we aggregate around 9,000 of electricity producers, consumers, and storage units, and control them according to signals from the system operators or price signals from the energy markets. The VPP orchestrates the DER, the distributed energy resources, to provide cost-efficient and secure electricity supply and guarantee a stable grid. Since 2009, we have operated a VPP, including around 9,000 energy producers and industrial consumers in various electricity markets. These are the wholesale market and market for ancillary services in 8 European countries. With a connected capacity of over 8 gigawatt, the VPP takes a significant role in integrating renewables, and this is also the title of our webinar. And these kind of renewable energy generators are mainly photovoltaics, wind, biogas plants, hydropower plants, and CHPs. In Next Kraftwerke, we believe that the energy system of the future can be 100% renewable. So therefore, we develop smart and digital solutions by intelligently connecting existing potentials and trading the flexibility. We link, in fact, different types of renewables and flexible power consumers and producers so that each unit supports the energy transition. To us, renewable, sustainable energy is not necessarily synonymous with unpredictability. We'll address this also today during our webinar. In fact, we specialize in short-term trading. So Next, Kraftwerke makes the flexibility of renewables a profitable asset and therefore furthers the integration of renewables into the grid. By utilizing full potential of digitalization, we connect thousands of energy producing and energy consuming units to our virtual power plant. We hope for a cleaner future, and we want the VPP technology to become the tool that the world utilizes to advance that goal. So for this reason, we would like to share also our experience through these webinars. In today's webinar, we'll show how VPP integrate renewables into the energy system. We'll do it on a real example of transition of the energy system in Germany. We'll showcase how energy system with increasing share of renewables can profit from advanced VPP technology, as well as how asset owners and VPP operators can capitalize on supporting energy transition by protecting the grid against the fluctuations associated with volatile energy sources. We'll do that on specific examples of renewable energy producers who are part of our virtual power plant. Additionally, we will show our VPP technology and how it can deliver multiple and various value propositions for different types of assets and market actors. Today's speaker will be a colleague of mine, Felix Jedamczyk. As a part of VPP Business Solutions team at Next Kraftwerke, Felix has gained insightful knowledge regarding key factors to successfully implement VPPs internationally. He has a very nice experience in assisting energy companies in developing their own virtual power plants. The presentation today is expected to last 45 minutes. And at the end of the presentation, we'll have 15 minutes for your questions and answers. the questions, we would like you to ask them in the chat in this Zoom meeting. Before I hand over the microphone to Felix, I have a few housekeeping conditions to cover. So today's webinar will be recorded and is going to be available together with the presentation slides on our website. You will get the link to access this information in a follow-up email. Second of all, you'll remain muted during the whole webinar. Nevertheless, we'd love to hear from you. So as I said, feel free to submit any question that may arise in your in the chat option. We'll be monitoring the questions during the session, and we will choose the most interesting of them to be answered at the end of the webinar. Due to time constraints, we of course apologize if your question is not going to be addressed during the webinar. In this case, we may get back to you afterwards individually or make the FAQ document on our webpage available, in which we'll wrap up the questions asked during the session. So I hope that this webinar will be insightful to you. And Felix, if you may.
Yeah, thanks, Alexandra. Thank you, everyone, for having me. It's a privilege to introduce a topic to you today, and I'm very impressed about so many interested people. So the first webinar focused on the business modules of virtual power plants, so how to earn money with VPP. And today I want to answer the question, like, why do we earn money with VPP? Why is it needed? And what are the key achievements of VPP technology? What is the basic requirement in a system with high penetration of renewable energies? So let's get to it. I would like to start the webinar with a direct look inside the VPP operation of Next Kraftwerke. And this is a geographical map of our pool, basically. As you can see in the legend, each colored point symbolizes one technology. So we have in yellow ones, solar power plants. We have the green ones, which are biomass plants, nearly 4,000 in our pool. We have hydropower plants in our pool. We have even consumers, power-to-X process that are taking part in the flexibility market. So a bunch of different technology. So this is our pool perspective. And at the same time, this is more or less a reflection of how the energy system in Germany looks like. And this constellation of assets is a configuration that a system operator's control system engineer would not particularly like. I mean, actually, this image looks chaotic, random, and very difficult to manage. But this is precisely where Next Kraftwerke's business comes into. We do like this configuration as we have the technology to efficiently and effectively manage and organize these chaos. Nevertheless, this increased complexities in energy systems is also the reason why there are justified discussions and concerns about energy systems transformation. The implications of this development are significant and challenging for energy systems worldwide. So it's a hot topic nowadays. So let's dive into. And the discussion comes from the evolution of the energy system during the last years. So in this example, we can see how the number of power plants in Germany has multiplied 2,000 times. So whereas we had 8,000 power plants in 1990, we nowadays have 1.6 million in Germany. So this is a dramatic change in the number of assets we have in place in Germany. And this is, let's say, the jet stream we are right now in Germany, but not only in Germany, but also in the world. Further, new power plants are based on renewable energy sources, which generation is difficult to predict. We have the nuclear phase out and change in the energy mix. So whereas we had conventional power plants, gas, nuclear, coal-fired power plants, we now have an increasing number of renewables, wind, PV, and they are like directly dependent on the weather circumstances. So it's quite difficult to predict. Similarly, the energy markets have been unbundled and liberalized, and we now have up to 12 different open spot markets in the world, in Europe. So we as private company being certified for this power exchange market, we can trade electricity. It's an open market for everyone. And the energy systems are in constant evolution, not only in Germany, but worldwide. And in fact, the world is undertaking a heavy digitalization process, as we can see exemplified in the number of LTE connections worldwide. And the digitization is, for us, I mean, an enabler to deploy digitized use cases based on VPP technology in certain market environments. So let's see the next slides to explain this increased complexity present in current energy systems. So this is probably the most fundamental basic rule of the energy system. This is something you initially learn when you cope with energy system. The grid needs to be balanced at any point in time. And a stable energy system requires nearly full synchronicity of production and consumption side. And otherwise the system will collapse. And this is one of the main purposes of system operators, to synchronize energy injection and energy consumption to guarantee a reliable energy supply to its citizens. So in 1990, keeping the grid balance was easy, since there were just a few large producers and the consumption side was more conventional and predictable. Therefore, the system was very reliable, it was dispatchable and very predictable. Now, in 2020, things are getting more and more complex. There has been a dramatic switch in generation as a larger share of renewable contribute to the energy mix. This means that the generation is more spread over the territory and that many DER have to be managed. But most importantly, that generation is intermittent and not easy to predict. So the weight of the left side of the balance is actually changing dynamically, and due to the decentralization, system operators even don't know which assets cause the change. So we have a lack of information about the asset, plus a lack of forecast expertise. And on the other hand, though, the consumption side has also evolved, and in this context, a new participant in the energy market was born. It was the prosumer. A prosumer is a flexible consumer which is also capable to inject electricity back to the grid. So even the consumption side is changed, which is actually good, because even consumers can help smoothly integrate renewables by offering and providing flexibility to compensate imbalances caused by renewable energy resources. Well, let's quickly summarize the first slides by saying that we can identify three main factors to guarantee the balance of the grid and to deal with the increasing share of renewables. First is awareness. So we really need to open this black box of decentralized assets. We need the live data, we need current status information about the assets, we need to know is the asset generally available, is there an outage, etc. This is key success factor, to be aware of the current production. So as the saying goes, prevention is better than cure. What I mean is that it's best to do it's good to do the best to do what you can to predict the production and consumption as precise as possible before physical delivery of the energy, in order to prevent a greater physical imbalances in the grid. And then we have secondly, the flexibility. So in case there are some imbalances remaining after trading and forecasting, then you really need to physically activate reliable capacity, ramping down assets to stabilize grids. This is something you can do with flexible assets. So flexibility is very important. And then the third one, speed. The flexibility needs to be provided very fastly, within seconds, minutes, or some minutes. Yeah. So with formula, next copes with the physical imbalances in the power system. To showcase how this is actually managed, I would like to showcase this example about a hydropower plant operated in 2010. Hydropower plants have an intermittent production, so also independent or dependent from the weather. But unlike other renewable energy resources, the production can be from time to time controlled. So meaning that the generation is flexible in a way. In 2010, the TSO was responsible for managing the electricity produced in the hydropower plant and to trade it on the power exchange. At the same time, though, the TSO did not receive live data from the hydropower plant and was not capable of remotely controlling its production due to the fact that the plant was not interfaced to any control system. And further, the forecast was made only once a day based on historical data. And therefore, the hydropower plant's operation was not optimized at any level, and the TSO simply decided how much energy to produce and to sell on the market every day based on a fixed schedule. So this offered no possibility to take advantage of the flexibility of the hydropower plant. And imagine you have millions of these power plants, no interface, no controllability of the assets, and millions of spread energy resources without any information about the status, the current production, etc. And even worse, these resources can do whatever they want to do. Nobody could potentially intervene in case we have excess of electricity. So now, in 2020, the very same hydropower plant can be networked into a virtual power plant. This means that the operator of VPP has control over the plant and can steer it remotely. The operator receives live data, so the VPP operator receives live data from the plant, for example, active power, state of water tank, etc., etc. And thanks to live production data, the training team of the VPP can validate and improve generation forecasts several times in a day. Because of this, the training team can more accurately sell generation electricity from the facility and can also manage their balancing cycle more precisely. Moreover, in Germany and Austria, next Kraftwerke uses hydropower plants to deliver a balancing reserve capacity to the system operator. Like, how does it work? On a signal triggered from the system operator, meaning when the system operator requests balancing reserve, maybe caused by a surplus of wind electricity in the grid, the VPP then activates its flexible capacity by splitting up this signal coming from the system operator and sending out individual set points to hundreds or thousands of assets to ramp down according to this incoming signal. So on this slide, you can see the different markets embedded in the time sequence until the physical fulfillment of the energy. Renewables are generally promoted on the power exchange, particularly on the spot market, like a day before delivery of the electricity. So without having any interface to the DR, without having live data, in 2000, the TSO trades, or 2010, the TSO trades the electricity, like basically the forecast profile, on the day-ahead market, just once. And however, there is this existing intraday market, which has a gate closure 5 minutes before delivery of the electricity. So you could potentially solve any problems you have from the day before the delivery of the electricity until 5 minutes before the fulfillment of the electricity. So this is a very powerful instrument, this intraday market. And let's see why. So this graph shows like a typical PV profile from a German solar power plant. And this graph shows the difference between like the day ahead forecast, this is the green line here, and the live intraday forecast, which is the gray line here. And you have in dark green the live in-feed of the PV power plant. So as you can see, the short-term forecast is much more accurate than the day-ahead forecast. And this is because, while the day-ahead forecast is only based on external data obtained from companies specialized in weather forecast provision, and also based on like static data, the angle of the PV power plant, the irradiation, etc. This is the initial forecast made for the day-ahead market. But the intraday market forecast, the continuous forecast until very close before the physical delivery, is based on the live data that comes directly from the asset. And this is the big fundamental advantage here we have with virtual power plant technology. The interface that is there to source live data continuously, and to continuously also update the forecast to be as accurate as possible. So this is like one of our customers in our pool. We do not own any assets. We just interface and promote the assets on the market. Well, we can conclude that any intraday deviation from the initial forecast can possibly balance on the intraday market until 5 minutes. We've heard that before, physical fulfillment. So this is what actually happens with the PV power plants. The formal imbalance here on the slide can be managed on the intraday market. So this deviation can be managed here. And this is the difference to the former years where just a system operator puts the day-ahead forecast on the market and just once. Well, I mean, at the same time, the reality is that there are still imbalances remaining after gate closure. And thus we have already identified that flexibility and speed is also key, meaning we still need reliable, flexible capacity to also physically balance the grid as a very last possibility. To finish the introduction, let's agree that the most important factors to better integrate renewables into the system are visibility. So we really need to open this black box. We need to be aware of, we need to monitor the pool of 1.6 million of assets located in Germany. This is pretty important. This leads us to the predictability. So we need to forecast renewable energies, especially the volatile ones and intermittent ones. This is a key factor here. And then if in case there are any deviations left and remaining, we need this physical controllability of flexible assets. And this is this cycle of optimization which VPP technology can contribute and deploy. Being aware, sourcing live data, predict the asset, and in case there is still something left, control the assets according to price signals from the market or physical signals from the system operator. So now let's go into the operations a bit. And in this part of the webinar, I would like to show you how it works in reality and what systems are part of a VPP operation. I mean, we have seen the theoretical example of a hydropower plant and of a solar power plant. Now we are going to follow some assets its way through the VPP. I mean, what is happening operationally? But first, here a brief overview of the ecosystem, let's say, of a VPP. It's not one fits all. There are a bunch of historically grown software applications and systems. So, for example, you have on the right side the assets in the field. The assets in the field are interfaced and networked via either an Xbox, this is a hardware case, remote control device, or non-hardware based interface, preferable standard interfaces, to a very powerful central control system. This is the NEMOX Next Monitoring and Control System solution, and this is basically the heart of a virtual power plant. This is a very powerful data platform to enable a very high frequent data processing to other software applications in this ecosystem. For example, for the forecast, the live data is coming into the database of the control system and then will be directly provided to the forecast application, for example, or directly to the market interface, the trading application. So whereas the trading is the market interface and the commercial instrument to execute use cases to the market, the NEMOX control system is purely the technical system and solution to aggregate, monitor, and control assets in the field, and not a few assets. We are talking about thousands of assets in any point of time, and doing this in a very high performant way within 1 second. So the signal is coming in, will be processed, and then the other way around, the set point goes out to the asset individually, and this cycle of optimization only takes us 1 second. So doing VPP operations, we are also willing to let the asset owner participate in the activities of a virtual power plant. Therefore, we have this customer portal here, which is the interface and a kind of communication platform to all the asset owners we have in the pool. So basically, the asset owner can see invoices on the platform, but you can also announce unavailabilities. So we really want to motivate and incentivize the asset owner to participate in the activities of VPP operations. So yeah, let's assume the plant is interconnected to our VPP, and now I want to start with an insight into the systems we are using, and I want to start with the central control system Nemox. Give me some seconds to open the application. So this is a desktop application, and at the same time, this is a demo, to be honest. So me as business development manager, I do not have the permission to access to this critical infrastructure of Next Kraftwerke. This is only something for the control system engineers. But this demo actually shows you pretty good what the functionalities are about. And this is also a system we are one-to-one using in our VPP operations. So let me prepare something for you, just an initial dashboard. Again, we want to highlight and monitor. I mean, this is our first purpose. We here see, again, a geographical map of our pool. So just artificial, but this could be the reality here. So each colored point symbolizes, again, one technology. We have in yellow one, solar power plants, biomass in red, and wind in blue. So this tool here is a very powerful analytics tool. So being aware of monitoring means that the control system engineer or the trader needs to select and analyze certain clusters in the pool or some technologies, etc., etc. So this is something I can now show you by saying, okay, let's concentrate. We have overall 4 system operators in Germany. This is Germany, divided into 4 areas. And we just want to highlight all the assets that are located in the control system area, a system operators area of 50 hertz in the eastern part of Germany. So let's do it. We do this database query. We say, okay, all entities. We want to filter by type. The type is here is a system operator. We want to select a certain system operator, which is 50 hertz. And we want to see all the entities connected to the system in 50 hertz. So here we are. This is all the assets, 200 assets we have interconnected in the area of 50 hertz. So now let's assume the system operator or the control system engineer wants to highlight just one technology, for example, just the biomass plants. So then we can also add a database query saying, okay, we just want to highlight a certain technology. We want to highlight biomass plants. And again, we want to see all the entities under the biomass technology. We execute. And we have left then around 810 overall. So we have to now intersections so that we have combined the 2 database queries. And we see in this control area, 50 hertz, we have 60 assets that are biomass plants. And maybe a last step into this analytics, maybe we just want to highlight, okay, what is happening with all the power plants that have an installed capacity less than 500 kilowatt. Maybe there's a law or a new regulation that counts for this asset class. So again, here we select, we say, okay, let's filter a signal. We filter the signal maximum power. Here we are. We say, okay, smaller or equal than 500 kilowatt, and we execute. So now 37 assets are left. So this is a geographical dashboard. More importantly for the system engineers is the so-called entity overview, a list of all the assets selected, and then we can select different signals we want to visualize. I've already prepared something in this test set of signals, and now you can see in the list perspective, a list of all the assets selected, and then, for example, some status information about the asset. So what is the current interface quality? So the interface to the asset is working well. RTU is defined as the remote control device. Maybe we also want to know, okay, what is the general availability of this particular assets in terms of the controllability of the algorithm. So then we can go and say, let's highlight the availability. Also status information. It shows up here, we can put it to the front, and we see, okay, all the assets in this list are currently available to be controlled by our algorithm in the control system. As well, we have here the activation command and the activation confirmation, meaning that when the point is colored in green, the algorithm is currently controlling this asset, maybe due to the fact that the system operator is demanding balancing reserve capacity, and the algorithm selected this particular asset to take part in this market. So in addition to that, we also have dynamic data like the active power, the current active power of the asset, also the maximum power, the minimum technical power, etc., etc. So let's dive into a single asset dashboard. By right-click on one unit, we can show details, and the asset dashboard will show up. What you see here is a graph. The green line is visualizing the current production of this power plant. It's a biomass power plant, as we have selected. It's according to a certain subpool in 50 Hertz. So the current production of the asset. And also you see again the status information. So it's quite stable, the production, very easy to predict. On the right side, you can see all the signals you can potentially visualize. For example, a power set point that comes from the algorithm. You can check and uncheck everything you want. So being aware means also not only the live perspective, but also the historical perspective. So let's go 2 days back until today, apply for it, and now it doesn't look very stable any longer. So here we see some down rampings from the asset. So why did the asset ramp down? We can highlight certain sections, for example, and see, okay, here we have the activation command, several activations coming from the algorithm directly. The asset reacted according to the signal coming from the algorithm, which can be visualized here. And to maybe highlight this section, according to the ramp speed of the asset, here again, the asset is fulfilling and trying to fulfill this direct command and set point coming directly from the algorithm of the pool. And this is something which is happening with hundreds and thousands of assets simultaneously. So the first point, information, visibility, predictability, without having steering capability. What else can we do? I mean, in the operation, we have an fully automated process in the backend. But just to demonstrate how it works, like in case the forecast application needs the live data continuously, we can here like select active power. So here we have a list of all the entities in the pool, and we have the signal active power. We want to have the raw signals. We put it in here, and we then can start the export and create a CSV file, maybe also for the billing system or something. And then we can store and provide the data sheet to the persons that have use of it. In the reality, as I said, this is a fully automated process. So the next step of sourcing the live data of the network system would be, for example, a trading application or a forecast application. So this is a visualization in the forecast application. Here again, you have the PV power plant or the PV profile, typically for Germany, and you have different forecast profiles here aggregated. So you have the day-ahead forecast, you have the intraday forecast, so you have the live feed-in of this PV power plant, and you have the live continuous forecast of the asset. So this is basically something which the forecast application is calculating independently from the central control system. The central control system is here, it's just the data platform to serve the forecast system. So let's do one step further and see, okay, we now recognize that we have a deviation in the forecast. What is the result? We need to balance our portfolio. And therefore, we here have next trading, which is a portfolio management system. And we go into our portfolio, for example, in Germany, and we see here that you have two graphs. The graph below is in blue the trades we have already done. The gray, let's say, graph is in this case a consumption profile, forecasted consumption profile, and the result of the already traded volume and the consumption profile is the imbalance or the balance of the portfolio. And what we do now is, or what the trading is doing now, is an order to balance the portfolio. Clicks on order, and we go to the intraday market. We see there live prices of the market. So each quarter hour has a price, a sell power price and a buy power price. And then we have here a list of the imbalances. We just select the imbalance, type in 3.2, blah, 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 and then we execute the trade, and the portfolio is in a way balanced. So this is a way, basically, of a renewable energy plant that only needs to be traded and where we really need to be good in forecasting. And now I want to also showcase the possibility of controlling assets remotely and helping physically to stabilize the grids. You can do this either on individual asset level, or you can do it on a pool level. The pool level is much more complex. So let's start with the individual asset level. We can highlight one particular asset, for example, here, generation. So here again, you see the dashboard of the asset, you see the current production of the asset, and the first step is to enable the algorithm to do remote controlling, saying, okay, we activate the general availability. And then we could potentially set a set point, saying that maybe we want to ramp down the asset to 500 kilowatt. We type it in, we have 500 kilowatt. We have here the new set point, which is basically a manual advice to do. I'm now control system engineer, and the asset is following this signal accordingly. Same procedure we could also do by just uploading a profile. So potentially we could also optimize this asset according to the price volatilities. Imagine you have a trading team that are doing price forecast, price prediction for the next day. We could potentially optimize the production of this asset according to the price volatilities, meaning in very expensive time slots, we will expand the production of the asset. In very cheap ones, we will decrease the production of the asset. This is basically something we can do by just uploading a file. We put the CSV file into the application. The CSV file will be uploaded and then will show up here as a new schedule and profile for the asset. In addition to this, and this is the, let's say, most complex approach for virtual power plants, doing scheduling and optimizing of assets individually, and in addition to this, providing balanced reserve capacity to the system operators. This is something we could actually also show you here. There's a certain product, the FCR, which is the fastest reserve power product in the market. Here we directly correspond, or the asset directly corresponds to the frequency in the grid by having a local frequency measurement device in place. So let's see, we have the frequency. We create a second axis. We here now have the frequency. The target frequency in the grids is 50 Hertz. So we put the 50 Hertz in line with the actual power production. And we see that, the way around, we see that the frequency is continuously volatile according to the initial balance we have seen, right? So according to the amount of electricity fed into the grid and consumed on the other side, the frequency is also pending around the 50 Hertz. So in a situation when the frequency is under 50 Hertz, there's really a lack of electricity in the grid, and we need to support the grid by activating positive capacity, and the other way around, right? When the frequency is over 50 hertz, we need to ramp down, for example, producing electricity, producing assets. So now let's activate the FCR for this particular unit. We activate it, and we now see that in addition to the schedule here, the asset is ramping down additionally because the frequency now is over 50 hertz, meaning that a production side needs to ramp down and stabilize the grid doing so, and stabilize it indirectly. So this is an example for having a very complex approach of combining different use cases in the market. So again, this is also in reality a fully automated process. It's not manually done, it's just for you for demonstrating purposes. So let's highlight the same approach on pool level. So what you can see here is the head application of our FRR ancillary service pool or balance reserve power pool. So what you can see here is the aggregated, the green line, the aggregated delivery of balance reserve power to the system operator. So the red line is the overall set point coming from externally from the system operator, and the green line is what all the assets in the pool are doing according to this red signal. So let's play a bit system operator. We see that we have a negative available balance reserve capacity of 150 megawatt and positive 40 megawatt. Let's just assume, okay, we have too much electricity in the grid and we really need to ramp down the production. We can activate 50 megawatts manually, and we now see that here is a new set point coming in, and the assets are reacting accordingly. So again, let's highlight this reaction on the pool maybe in a certain cluster we have aggregated. We drag and drop, we put the assets over to the other section, we activate the test, and we now see that most or many of these assets are taking part in this delivery and this call from the system operator. Meaning that, again, the unit dashboard, we can see having the new set point here. This is what I actually did on the aggregation pool level, but split it and divide it to the asset level. So this is basically our approach in the controllability use case in the end. And with look to the time, I would skip the customer portal, which is basically very interesting. But this is essentially what VPP technology is about, this central control system, which is powerful to process data, but also go the other way around back to the asset. Yeah, so we have seen the general challenges in an energy system with a high penetration of renewables. We have also seen how virtual power plant operates and what actually happens with one particular asset. Now, let me finally round off the topic from an economic technical system perspective, let's say. And I mean, did the system at least cope with the increasing share of renewables? Do we still struggle? What are the overall system costs? Let's first highlight the required balancing reserve capacity that the system operator in Germany can activate physically. So the pillars show the overall capacity in megawatt that the system operator were tendering per year. And each pillar composes of different balance reserve products. And the main distinguishing criterion is the activation time as well as the direction of control. And we can see in this graph that the required balancing reserve has been decreasing steadily in Germany in the last 10 years. And even there is a higher share of renewables present in the system. So if you would have asked us 10 years ago, most likely even we would have predicted the opposite development. And I think this is really astonishing because, I mean, because it proves that nowadays we are capable to do very accurate forecasting, and we can manage most of the imbalances already on the trading side. So also it indicates that both the consumption side and the production side improved adaptability, meaning both sides adapt to the other side, mainly driven by price signals from the spot market. One can say that price signals are an image of the physical status of the grid. Surplus of electricity leads us to low prices on the spot market and the other way around. Before we move forward, let's go one step deeper. If you look at the development of the different products, it's obvious that the gray ones decreased significantly, whereas the rest decreased less. And actually, it is the MFRR, the slowest balancing reserve product. We have 15 minutes activation time. This also indicates, let's say, that systematical imbalances can be already managed before. Let's now jump to the costs. I mean, each diagram here shows one particular balancing reserve product, R1, R2, R3, or the different definitions I've already told you. Each pillar shows the costs in million euro per provision of the balancing reserve product. And at the same time, the cost, these are the costs for the system operator, I mean, respectively for the citizens, because these costs show up on everybody's energy bill. These are the potential revenues for VPP operators who are providing ancillary service or balancing reserve power. What we see is that costs decrease significantly. For us as VPP operator, profiting from the market, it's nearly dramatic. But this development is due to the higher competition on the market. And the market for balancing reserve power is fully liberalized. Everybody that fulfills certain requirements can potentially take part in the market. And this has led to a rising number of market participants, but also to a rising number of flexible assets taking part, especially small and medium-sized assets. So required capacity decreased, which is a good sign for the system. And also the cost decreased, which is also a very good sign for the system, because this means that the system is pretty much cost efficient. So what is about the reliability? Just briefly, this is a SAIDI index that shows the average outage duration in minutes each customer served. And we see that even this number has improved. There is no negative development we can notice over the last years. And I mean, the renewable energies, the share increased, but even though we could manage the grid pretty secure and reliable. The power supply for German citizens is pretty reliable still. So this graph wraps up the system analysis presented in the last slide. And here we can see how the market activation corresponds with the steady rise of the renewable feed-in. So while the feed-in of wind and PV, the intermittent one, increased continuously, the call for control reserve, so the activation of capacity, decreased significantly. Significantly. This means that the system participants can more effectively trade in the intraday market to compensate the deviations between the generation and the demand. And the result of this is that the balancing services are required less times and in smaller volumes. And as we have explained in this webinar, this is achievable due to the better prediction services that are available in the market nowadays, and thanks to the ability of remotely controlling flexible assets. So just one figure here, this is the amount and the trading volume, which is significantly increasing over the last years. So we have a change of the volume from the intraday, from the balanced reserve power market towards the intraday market. Things can be solved very early on. So yeah, just briefly an overview here. Improving forecast quality and increasing intraday liquidity means, I mean, we have less balancing reserve capacity. We have a more cost-efficient market right now, having VPPs in place, and the result is following here. Yeah, so this is all from my side. Many thanks for your attention. Let's jump to the questions.
Yes, thank you, Felix, for this very insightful presentation. I saw that there were really very interesting questions in the chat, so let's jump to them right now. If you can please stop sharing your screen so that I can start sharing mine.
Sorry.
That would be really good. Yeah, no worries. Okay, we have them. So first of all, there were some questions about trading. So the first question was if intraday can be traded up to 30 minutes beforehand, how is the 5-minute granularity of PV live forecast fits in? And it also is quite linked to the question that was asked during the registration in the registration form by one of the participants. What is the granularity of weather forecast data or the forecast data that is required by the virtual power plant? So maybe also very short disclaimer in this question. In Germany, we can the gate closure is in fact 5 minutes before delivery, but that's just a one disclosure, and I hand to Felix now.
Yeah, exactly. Thank you, Alexandra. This is actually what I wanted to also to say, and apologize at the same time. This was a former slide. Market has developed, and now we have this 5-minute gate closure on the market. In the former years and times, what was 30 minutes. So this is the basic granularity, the 5 minutes gate closure, even though the product on the market is a quarter hour. So we need to trade and forecast at least a quarter hour. So this is the focus like time slot we can forecast and predict, because this is the smallest product we can trade on the intraday market. And the granularity of weather forecast data, for us, the higher the granularity is for us, the better we can predict the production profile of PV and wind. So what we have is an instantaneous data sourcing from the assets. In case the signal or the production is changing, then we will get new data directly coming from the asset in the field to directly influence and improve the forecast application for PV and wind. So granularity is good in terms of the live data. In the end, going to the market, we have this fixed structure of quarter-hour products.
Mm-hmm. Okay, so let's go to the next question. Very interesting one. In case of hybrid power plant, wind, solar, and battery, or wind and battery, do you diversify in your platform the capabilities by technology, or do you treat them as one black box system looking only at the total exchanges to the grid interface?
Yeah, very good question. This is also a discussion about the use cases. So once you have signed a contract with an asset owner, let's say a PV power plant owner, a PV power plant is not really flexible. You just can ramp it down. So it's not capable to offer balancing reserve service to the system operators. So this is the first step, being in discussion with the plant owner and seeing, okay, evaluating what is the fitting use case for you, and then allocating each technology to the use case we can deploy. So in the last webinar, we have seen, okay, there's the balancing reserve power market, there is the trading side, maybe there's also the individual optimization based on price predictions, etc., etc. So in the end, the asset or the technology and its, let's say, technical restrictions and the behavior decides a bit which market to approach. This is basically something we do before signing, because the contract is about a specific use case in the end. And then once the asset is interconnected to the pool, and then the asset is already allocated to a certain use case. And one use case is then, let's say, the balance reserve use case. Then we have a pool optimization, and the algorithm is fully automatically optimizing the full pool consisting of different technologies which are taking part in this specific use case then.
Mm-hmm. Yeah, but we can also maybe say that for our own VPP, once we sign the contract with an independent power producer, then we rather know what kind of technology is behind that grid point, right? So it's very rarely a black box. What would you say?
Yes, I would agree totally. I mean, we have experience, we are doing this since 10 years, and we have discovered several technologies and the fitting use case for it. But even though, I mean, there are several use cases in discussion, so what about local flexibility? What about small-scale residential flexibility, behind the meter flexibility? These are upcoming new business cases, which also we need to adapt to, and we need to figure out, okay, do we have the right instruments from a technical perspective to also deploy these new upcoming use cases? So it's always kind of organical evolvement of our systems.
Mm-hmm. Thank you, Felix. The next question is probably a very short one. What kind of devices do you have on the asset premises to control these assets?
Yes, we have basically a remote control device, an Xbox, which is composing of an SPS, a GSM or a modem, a router, and potentially also a frequency measurement device, composed and equipped in a hardware case, and then provided to the asset owners. And the asset owner then install this hardware case on the asset. You can imagine that this is not really cost efficient when you want to integrate a wind turbine or PV power plant with, I don't know, several hundred kilowatts. In this case, we prefer to interface via a non-hardware based interface. For PV power plant, for example, the inverter do have already kind of prepared interface, a data logger or a SCADA system we can directly interface to, and then we realize a VPN tunnel, and we have this bidirectional communication interface without equipping the site with hardware. So several opportunities according to the assets, the technology, and also again the use case. So the hardware case is, for example, mandatory for the use case of reserve power. So it's a mix of all, and each asset, let's say, is a single individual project, and we then have a team. They do day in, day out, just like integrating and seeing how can we interface to certain technologies.
Mm-hmm. And the next very linked question, does Nextbox work as a smart meter? That's one question. And the other one, who takes over the costs for connecting the asset through the Nextbox or the data delivery through the VPN?
Yes, the Nextbox is not a smart meter. So we don't have a measurement device inside the Nextbox. The Nextbox is just taking the on-site metered data and providing it to the control system database. If we have few projects where we also put a meter, not a certified meter, but a meter device into the Nextbox, but this is not the common way to do, because in the end, we just need the live data, and it doesn't need to be certified officially because it's in our internal use, the data. We just need it for the forecasting, for example. The second question, will take over the costs. It's like full package service. Once we sign a contract with the customer, either the customer needs to pay kind of initial fee to interconnect, but usually we have just one direction of revenues or costs from the virtual power plant operator, revenues back to the asset owner. So meaning that we can also calculate and overlap the revenues we are generating and creating on the markets. We can overlap the costs, and then the asset owner isn't really doesn't see any invoice and do not have any costs.
Mm-hmm. So maybe very shortly summing up, Nextbox does not only meter or measure the power output, right? It can also steer the devices in a very precise way. And who takes over the cost of connection? It's the asset owner, but the cost is uncomparable to the revenues by the asset owner, and the, let's say, the time of the return or the payback time for this initial investment is very short at the end of the day, because the revenues from delivering the ancillary service are significantly higher, right?
Exactly. Yes.
Okay, great. Very connected question as well. Again, we are staying in the area of balancing services. And the question is following: every TSO signal can probably be achieved by a different combination of assets. How does Nemox choose among these variable assets? Do you guarantee to all assets owners that they will be chosen and remunerated with similar frequency? And there was a very similar question from the registration. Will Nemox automatically dispatch the commercially, technically best fitting asset based on the trading results results out here modified based on the ancillary service? Let's stay in the area of ancillary service.
Yeah, also a very good question. This is about how the algorithm works operationally. In general, the algorithm needs to take into account several restrictions. So let's begin with the technical restrictions of assets. So you have ramp speeds, you have minimum technical powers, etc. So that's something the algorithm needs really to take into account. And then you have like commercial aspects. For example, the activation costs of different technologies. And this algorithm also takes into account by having like priorities in activation. So that assets with low activations costs can be activated more often. Then there are like, let's say, smooth restrictions that comes along with, okay, we are operating a solidaric pool. Everybody who's taking part should also benefit from the market. So we also try to let everybody participating on calls of the system operator. So overall, it's a bunch of different restrictions and constraints that the algorithm is continuously taken into account. And by the way, again, 1 second, taking all these millions of signals and restrictions to calculate something. And yeah, maybe also this answers the second question. It is an automatic process, but it's not only the commercial perspective. There are several restrictions coming from the technical side, from the commercial side, but also coming directly maybe from the asset owner who has certain ideas or interests. These all these restrictions are taking part in the algorithm's operation.
Mm-hmm. Also, maybe it's quite worth to indicate that the VPP operator can also, let's say, arbitrarily assign some priorities, right, to the assets in our NEMOX system.
Yes, we can do. I mean, there are priorities, mostly according to the activation costs for each technology. So you can like manually also adjust the priorities, maybe when there are additional arbitrage constraints or something. Always in discussion directly together with the customer.
Mm-hmm. Thank you, Felix. Now let's go to the question of the demand side, a very interesting one as well. As a VPP customer in Germany, or do you also have in your portfolio industrial customers who want to offer demand side response? If yes, in case of undersupply, how does NEMOX decide whether to shift the load from a consumer or increase production from an asset?
Yes, we have demand response assets in our pool, mainly big industrial sites. So we are talking about electrolyzer processes in the aluminum industry, for example, or chlorine industry, chemical industries. Due to the fact that they have a very constant consumption on a very high level, and you just can't ramp it down in a situation when you have lack of electricity. And when you then also have an existing GOT storage or something, you can really flexibilize the consumption of this asset. So yes, we have industrial sites in the assets that are taking part in the balanced reserve market. And here again, I mean, once the technology is aggregated to the pool and allocated to the use case balancing reserve, it's in competition to the other technologies. So then it's just about, okay, what is the activation priority? What are opportunity costs? What are technical restrictions? What is the ramp speed? And then the algorithm automatically selects, okay, in this call, maybe the site, the electrolyzer process of an industrial customer is the perfect fit for this call, because I don't know, the ramp speed is very fast and the customer can ramp it down very fastly. Okay, then we go for it. It's always like for the system, the control system, the system is technology agnostic. So it doesn't matter which technology is taking part. It's just about the restrictions and the framework within the algorithm can ramp down or ramp up assets.
Mm-hmm. Thank you very much, Felix, for your insight, for your answers. Unfortunately, we are running over the time, so I would like to thank you very much for your presentation, for your Q&A round. I really think that it was a very insightful session. And thank you to all the participants for participating in our webinar. We are very happy for such a big attendance. If you still have any questions or comments, or you would like to reach out to our team or to Next Kraftwerke, please feel free to contact us under webinar@nextkraftwerke.de. At this moment, we thank you for your attention, and we really encourage you to stay in touch with Next Kraftwerke, either by following us on social media or subscribing to our newsletter, or just visiting our website in case we will organize following webinars on this interesting topic of the virtual power plant. So thanks a lot, Felix, for your presentation. Thanks a lot to everyone for the participation. And I wish you a great day still ahead. So thanks a lot and goodbye.